Hello everyone, welcome to my tutorial on reinforcement learning, a very powerful branch of machine learning where artificial intelligent agents learn by interacting with their environments. They are all guided by rewards and consequences. But before we dive in, let's take a quick trip back in history to the early 1900s. In a quiet Russian lab, a man by the name Ivan Pavlov discovered something extraordinary. He discovered that his dogs began to salivate not at the sight of food, but at the sound of a bell. This led to the discovery of the concept which he termed classical conditioning, the brain's ability to form associations between unrelated events. The bell, in our case, a neurostimulus, had become linked with food, a biological reward, turning the sound into a very powerful trigger. The dogs had learned to expect by the sound of the bell. But now, imagine for a moment that the dog wasn't just sitting there reacting. What if the dogs could act? What if the dogs could choose when to press a button for food or decide to explore new strategies to get more treats? That leap from passive classical conditioning, from passive response to active decision making, is what brings us to reinforcement learning. In reinforcement learning, agents don't just respond to stimuli, they learn by doing, by trial and error, and by understanding which actions brings rewards. So in this tutorial, in this code alone tutorial, we will level up from foundational concept to powerful deep learning techniques. We are going to level from level 1 all the way to level 3. Level 1 will be our Q learning. Level 2 will be our DQNs, and level 3 will be policy grading method. So for level 1, which is our key learning, our journey begins where the agent uses a magical scroll, which is the key learning table, to remember the value of taking certain actions in different situations. It learns from experience, updating its map of the world slowly but surely. Level 2, which is our DQN. As the world grows more complex, the scroll becomes too large to manage. Then that's where we need DQNs. So DQNs approximate the Q values, enabling our AI agent to tackle massive environments, such environments that are complex, such as those of video games. So with tools like experience replay and target networks, the agent learns from the past and avoids costly mistakes. Lastly, policy gradient methods. Uh, in policy gradient method, we do not estimate Q values, but directly learn on how to act. So this method is very powerful in continuous and nuanced environments, perfect for tasks such as controlling robots and flying drones. So what we are going to do, in under Q learning, we are going to introduce the frozen lake environment. We are basically simulating walking on a frozen lake, and we want to avoid to fall into the frozen lake. In DQNs, we are going also to introduce the cart point environment. Basically, we are going to balance a paw on a moving cart by either moving right or left. And on policy gradient method, we are going to use the same environment, the cart point environment, but we are going to use a different model. So sit back, grab a cup of coffee, and let's learn reinforcement learning together. Thank you. Hello YouTube, welcome to my tutorial where we talk about reinforcement learning models. Now this is another tutorial, part of the many other tutorials that I've done already. I've done a tutorial on supervised learning models. I've done also a tutorial on deep learning models. But in this video, we are focusing on reinforcement learning models. All right, what is reinforcement learning? Reinforcement learning is a type of machine learning where an agent learns to make decisions by interacting with the environment. The agent takes actions, receives rewards and penalties, and updates its strategy over time to maximize its rewards. Reinforcement learning is widely used in robotics, in gaming, in financing, and in many other AI-driven applications. Basically, what reinforcement learning does is like you training your own dog. If your dog do what you want it to do, you give it a treat, a toy, attention, praises, and anything that allows it to continue to do the behavior that you want. On the other hand, if the dog behaves in a way that you don't want, you either walk away or you do not give it any praise or any petting to the dog. Over time, the dog will realize that this behavior is unwanted and this behavior is rewarded. So that will be your negative and the positive reinforcement. There are about 5 or 6 key components when you're talking about reinforcement learning. First one is agent, which is the decision maker, the environment, which is where the agent operates, the state, which is the current situation of the agent, action, the choices available for the agent, reward, feedback received from taking action, policy, the strategy that maps states to actions, value function, which is the expected long-term return of the state, then the Q value of the Q function, which measures the expected future reward for taking a particular action in a given state. In this video, we are going to focus on Q learning. Now, Q learning is a value-based reinforcement learning algorithm where an agent learns an optimum action selection policy using a Q table. The Q table in our case stores the expected reward for each state of action and updates based on the Bellman equation. I don't have the Bellman equation with me right now, but you can Google it up and look. It have got um, the symbols that you can that comes up to the formula, the equation. All right. So in our example, we want to traverse the frozen lake. I have just outlined it here. We want to traverse the frozen lake, which is this lake that you see in the background here. And we have our Q table, which is this table. So we want to train an agent here to traverse from the start, which is S here, all the way to the end. We don't want it to traverse to this H, which is the wall highlighted in red. Just like a human being traversing a frozen lake, we want a person to come from this end of the lake to the other end of the lake without falling into the water. Same thing in our case, we want our agent to traverse this grid from start to finish without going into these holes. So in our example here, the agent, they've got options to either go this way, go this way, go this way, or go this way. So we gonna train our agent, and if it falls in H, it's gonna be punished. But if it goes on F, which is safe route, it's gonna be rewarded. Then we'll see how it's gonna get to the end. So this is our project that we're gonna start on. I am going to head on to my Jupyter notebook to get started. All right, now I am in my Jupyter notebook. So let's go ahead and start this project. So in this project, we want to train our agent using the Q-learning to navigate the frozen lake environment. We wanted to find the best way to start from the end to the finish. So the agent must learn to navigate to the end, from the start to the end, while avoiding those holes, and also to maximize the cumulative reward. And like I showed you earlier, that frozen lake environment is just a 4x4 grid. We're gonna start from the start, and it will find the best optimal way to navigate from the start all the way to the end. All right, so our goal is to using Q-learning for those frozen lake. It's an environment given by OpenAI that we can use to train. So to maximize rewards. And we are going to use, in our case, we are going to use the frozen lake environment. All right, so I'm going to take this one to Markdown, run it, and let's go start ahead and import our critical libraries. So in this case, I would want NumPy, I would want Gym, I also would want Matplotlib and Seaborn. So NumPy, I would want also Seaborn. So Matplotlib and Seaborn, SNS, I use them for visualization. Okay, NumPy is a library for numerical computations, especially when working with arrays. In our case, we are going to work with the Q table, so automatically we are going to use NumPy. Then Gym is that's the OpenAI AI toolkit for developing and evaluating reinforcement learning algorithms. In this case, we are going to grab frozen lake from that environment. And again, Matplotlib and Seaborn, I'm going to use it to visualize. So what we want to do here is to create the frozen lake environment. So to do that, we're gonna do environment is equals to then our gym dot make, and we're gonna just specify the name here, frozen lake, which is our, in our case, our version 1. It's a string. Render mode. All right, let me explain this one. So gmake what it does is kind of initialize the frozen lake version 1 environment. So as I said, is slippery to false. It ensures that the environment is non-slippery. In the original version of the environment, the agent movement might not always be predictable. So, but with setting is slippery to false, the agent action would oh my goodness. The agent action will deterministically lead to the next state. Actually, when it's not slippery, it will allow the agent to traverse to the next step. Now I've set the render mode to ANSI. It actually specifies the text-based rendering of the environment. We're gonna use it's very useful when we do what you call console visualization. All right, so now I've done this. I want to initialize my Qtable. Qtable. Right, to initialize the Qtable, I want to specify the state size. All right, state size. So our environment, observation, action, perfecto. Let me do this. Actually, I need to do the other way. I can just delete this one and do this one. Yeah. So that I can have more space and push it up on the middle of the screen. Alrighty. All right. What do I need to do here? My Qtable. All right. So what I need to do here, or what you need to do, is to have your state size and action size here. So what we are doing here, we want to retrieve the total number of states in the environment. In our case, I've shown you this, the diagram. There's 16. It's a grid of 4 by 4, so there's 16. And uh, the action size, we want to retrieve the total number of actions the agent can take. So remember, if you do I still have it right here? All right, I closed the PowerPoint. But remember, the agent can traverse up, down, left, and right. So our Q table, now, if you see here, good catch. All right, so our Q table now, um, we want to initialize it one with dimensions of state size and action size, and fills it with zeros. The Q table will be used to store the Q values, which represent the expected future rewards for taking a given action for the specific state. All right, so now that we have initialized our Q table, we need to specify our hyperparameters. All right, to specify our hyperparameters, we have to have our learning rate. In our case, I wanna do 0.1. If you look at the Bellman algorithm, this will be the alpha parameter. Let me see if I can quickly Google it. Go rhythm. Let me see. Yeah, this is the one. So, oh, I went to YouTube. Let me, my goodness. But anyway, I closed it. Let me see if I can pull just a quick image. There you go. So now when we are setting our hyperparameters, we are actually doing this equation. All right. So the alpha, we are going to do the discount factor. We are going to do the epsilon max mean, and also we're going to do the decay, the episodes, and the max steps. All right. Let's go ahead and go back to our parameters. So discount factor, I'll set it on 0.99. 0.99. Alrighty. Let's do which is my initial exploration rate. Epsilon mean 0.01. This is the minimum exploration rate. So this one is the initial and this is the minimum exploration rate. Then let's go ahead and do the decay. I want to set it on 0.995, which is kind of a decay rate for each and every episode. Let's go ahead and do the episodes, which is basically the number of episodes. Max steps is equals to 100. Now, if you do not set your max steps, the agent will keep on traversing that grid. It will be like a while loop. It won't really stop. So we want to stop at 100. All right. You can set it of whatever number you want here, but I think 100 is a good so that it won't keep on. It will be an endless loop. We don't want that. All right. So let's go ahead and track the rewards. So I will start with an empty list here, which is I would call a reward list. I'll just initialize it at 0. Then I want to count what I call success count. It will be start at 0. All right, so I'm going to use that. So let's do our Q learning training here. Alrighty. So to do our Q learning training, what we need to do is I can do a while loop. Actually, let me go with a for loop. All right. So I'll use form episode in the range all the entire episodes. All right. Our state is goes to environment. And want to always reset that environment. Then our done, I want to set it on false. Then our total rewards, total reward. Right now, initial, it will be on point 0. Then I want to go again for step in range. Again, I'm going to provide this code in my GitHub. There will be a link in the description for my GitHub, and you can take it from there and modify it, play around with it the way you want. All right. So for step in the range max steps, what do we want to do? So I would say if run here, all right, then action, actually, dot action, in our case, action space here, then else action, my Q table here. I want state and everything. I'm kind of, I want to set the best action. All right, so now that I've done this, I want also to perform the action. So what I'll do is to do next state of my reward, next state reward, done. Is equals to an environment step, then this will be action. Alrighty. So if done and reward is equal to 1, what do I want to do? Then reward is equals to 10. I'm just rewarding the agent with 10 points. Then success, which is my initial variable, success count, I want it to be added with 1. Then elif, done, and reward is equals to 0. There is no good outcome. What do you want to do? Want to punish it, right? So reward is equals to -5. We are kind of penalizing the agent for falling into the holes. Remember, we are traversing the Q table. All right. Um, so what do we want to do? We want every move that is happening, we want to update our Q table. So here is what we're gonna do. So under this for loop, we want to go ahead and do Q learning, update rule. So it will be still under the action. So our state and action. Alrighty. Okay, Q table state action is equals to, then we're gonna do one, the learning rate, we want to multiply it um action. Let me add it here just for a new table. And okay, let me push it to the next learning rate times what do we want to multiply it by? We want to multiply it by reward, and also reward plus, I will say, my discount factor. Let me double check on this one. Yes, I want to multiply by discount factor, and also multiply by discount factor. Then, okay. Key table, then next state. All right. And again, I'm gonna add to this total reward. I wanna count the rewards, then state. Alrighty. Yep. State is equals to next state. Perfecto. So if done, what do I want to do? I just want to exit, so I'll break. And now again, we want our agent to explore. We want to explore when we initialize our agent. We want to explore, but over time we want it to pick the right pathway. So we want to lessen the exploration over time. So to do that, what I'll do is so my max. Let me think here. Okay. I want to append this one to the total reward. All right, let me see. All right, perfect. So now I will let me go ahead and print the progress. So node 1000 is equals to 0. What do I need to do? I just want to print my F string here, episode. Then I want to grab the episode and my total reward is equal to total reward variable. Then I also want to print the success rate is equals to, let me- all right, it's success count here, divided by the episode. Then I want to format it perfecto. All right, so the rest here is just I want to visualize to have that the Q table. I also want to visualize the rewards. So let me go ahead and visualize the Q table. And again, I want to visualize the rewards. All right, let me start with the Q table. So plot.figure, you specify the fig size, whatever size you want, doesn't really matter. So I'll go with an 8 and 6 here. Perfecto. I want it as a heat map. So the entire Q table the width of the lines doesn't matter, 0.5. Then the labels, all right, let me start with the X label. This will be actions. This will be against the stats. Yeah. And my title, it will be Q table heat map. Actually, let me also visualize the rewards. So to visualize the rewards, what I want to do is plot figure, my fig size is equals to whatever size that is comfortable with you. The smaller the better. In my case, we want my reward list. The color, whatever color you want, blue. I'll set the alpha to 0.7. I'm gonna plot the X label. This will be episodes. Episodes. The Y label will be total rewards. And my title it will be, actually, I don't want tutorial words in this case. Okay, tutorial words. Yeah. Reward progression over time. Then I just want to show this one. Okay, we don't need this one now. Dot show. Perfecto. All right, now let's render. Wait, okay, let's test the trend agent. And so my environment, which is gym dot make. What is its name? It's Frozen Lake. Frozen Lake, and it's version 1. Perfecto. I set it on is slippery. I set it on false. The render mode in our case here, we said it was set it on 0, and also currently done is set on false. Let me print the agent navigation. Agent navigation. Yeah, I can do that. I can just set it on a new line. Okay. While it's not done, action np we say is equals to my environment. Alrighty. Right, let's do, what do I need to do? I want to print the environment. And also just environment and close it. All right. The meat and bones of my Q learning is done. Alrighty. Let me run and see what we got. Oh, perfect. I thought I had several errors. Okay. All right. And also, alrighty. All right. It's not, I'll change the color here. Okay, let me also look right here. I can go with blue. I said cool on instead of cool warm. And also I will check the other errors. All right, what is it saying? Oh yeah. Let me just go back to and run. So what I'll do is I will also check the errors and see if it looks like it's stuck on the start. It's not traversing. It's not traversing. So it's, if you remember that, let me pause it and I'll see why is it stuck on the initial um, on the um, initial state. We want it to traverse the entire grid. All right. All right. So what I end up doing is I end up adjusting my learning rate and the discount factor, basically for better convergence, and also I also modify the Q table update formula so that for better learning stability. All right. So yeah, my results, and this the progress over time. It explores when it's starting, then it kind of knows where to go next. Then at the same time, this is my Qt heat map, and I want to show you how it is traversing. So start, it went down again, it went right, down, and G. So something like that Q table that I showed you earlier on. Do I still have it close by? All right. But let me see. Yeah, I'll put it on the screen. Oh, actually, I can quickly pull it up. All right. So what it did is it went down, down, right, right, down, and it took this route. Start F, down, down, right, right, down, and G. All right. So it went in an unknown environment, find the best way to traverse without going into these walls, and went all the way to the end. All right. Thank you for watching. I'm going to upload this code into my GitHub and see you on the next lecture. Hello everyone, this is my second code along project on reinforcement learning. But in this video, we are going to do DQNs. Our first video was on deep learning, on Q learning rather. So right now we are switching over to DQNs. But what are DQNs? Now, Deep Q network or DQN is a deep reinforcement learning algorithm that combines Q learning with deep neural networks. Basically, that's what it is. It was introduced by DeepMind in 2015, and since then it kind of revolutionized the entire reinforcement learning concept altogether. Now it's used in robotics, it's used in military applications, and many other applications that you might think of. So basically, I don't want to go into detail how deep learning works. I assume that you've already done your theory part of it. Now you're here to kind of have a hands-on project, understanding on how it works. All right, so the goal of our project today is to train an AI agent to become a paw on a moving cat using DeepQN. So our key objectives are to train a reinforcement learning agent using DeepQN to play the cat paw version 1 environment, to optimize the agent reward by maximizing the time the paw stays upright, to implement dwelling DQNs and double DQN for better stability and performance, and also to achieve reward score of 475 plus solved within 500 episodes. Now we are going to use the CatPo version 1 environment, which is a classic control problem from OpenAI Gym, where an agent controls the cat moving along a track with a paw balanced on top. I'll append a video so that you can see what I mean. But basically, what we are doing here is to we are balancing a paw on a moving cat. So we have two options. We can either move right or left. So depending on where the paw is leaning, we want the agent to move either right or left so that it maintains the balance. All right, so I'm going to jump over to our to my Jupyter notebook and start to code along. And let's get started and see what our agent will do. So remember, our goal is to solve the environment. The agent must achieve an average score of 475 plus over 100 consecutive episodes. I'm going to do a maximum of 500 episodes, but you can come up with whatever you want and make sure your agent works as you expect. All right, so let's get started. I am going to now, if you have not installed these libraries, so you're gonna pip install Gym, NumPy, all those. I'm gonna use NumPy. One random. We also want Torch. Actually, let me do it this way. Then, yeah, this is what we want. I've already installed them, so I don't need to install this. So I'm just going to import. Right, import. I'll start with Gym, where we're gonna get the environment. I want to import NumPy as np. I'm going to import random, import touch. Let's go ahead. SNN, import. Then from collections, import DQ. Perfect. All right. What I want to do here is to maybe increase the size a little bit. Perfecto. And I'm going to write the giant code for you, but you can do same by same if you want. So what we need to do here is to define. I want to define the dwelling deep Qnetec. So to do that, I'll do class dot module. Let's initialize it. I want my state size here and action size. Perfect. Self. Perfecto. Dot linear. Then state size 128. Perfect. Then self. Again, linear size 128. Basically, I'm defining. Let me define the value stream here. One to eight action size. Right, perfect. Actually, yeah. Then the advantage stream. want self dot value action size. Then under this class, we need to go ahead and do a function. All right. Self dot fc1 then let's go ahead and do, I'll copy this and do another x dot, this will be 2. Yep. Then let's do under the function value is equals to self dot value of x, then also advantage is equals to self dot advantage fc of x. What do I need to do? Let me go ahead and print. Actually, let me return this one. Return a value plus image. And I just want to subtract the mean. Actually, let me do advantage here. All right, perfect. All right, so what I want to do is to assign my hyperparameters. So to do that, we are kind of defining our formula. So basically, I am going to assign the number of episodes that I want, and I've already established them to be 500. Then the learning rate, and then gamma 0.99. So the mean here will be 0.01. Let's set the decay. I want it to be on 0.995. What about the memory size? Let's set up a larger memory buffer, 100,000. And we're left with batch size. My batch size, and we want to update the target, the frequency one set on 5. All right. So now we have defined the hyperparameters. Let's initialize the environment. We said we're going to use the CADPO environment from Gym. All right, so to do that, we're going to set our environment is equals to gym.make. We say it's going to be CADPO version 1. Where is it? I'll copy this one. All right. State size. So we want to have our environment. Shape will be 0. Let's do action size. All right. Our environment dot action space dot n. Now I want to go ahead and initialize the model. So to initialize the model, I need state size and action size. Then, okay. So to do that, I want to say policy GQN, which we set up here. So that's where we need our state size and action size. Perfecto. Then our target net. TQN state size action size. Then we're gonna go ahead. I'm gonna be a little bit faster now. Load state. So we want policy net dot state. Perfecto. Then target net evaluated. Then also optimizer is equals to optim. We're gonna use Adam policy dot dot net dot parameters. Our learning rate, we already set it. So I wanna let me double check what I set my learning rate to be. All right. Okay. I'm using Adam. Okay. Memory. My max lane. Let me double check what about 100,000. Okay. Perfecto. All right. Let's come up with a function to select an action. So I'm going to use double. Okay. All right. To do this now, I want to come up with a function. I'll just go and select action. So I'm going to do state if random is greater than, actually only less than, what do I want to do? On our return a random choice. So, okay. Else on the printout that I'll do, I'll save this code. I will also add some notes so that I can explain deeper when you do your follow along. I'll return on policy.net, and here I want state. Yeah, item. Now, let me use the upload function. Most likely, if you are doing you might use your MSC loss, but let me go ahead and use Haberlos, because Haberlos is kind of more, to me, it's more stable than MSC loss. So I'll just do Haberlos input target delta is equals to perfecto minus just target here. There it goes. Yeah. Then mask is equals to my error absolute value. Let me match it with a float here. All right. Oh yes, I'll wrap everything in the float. Okay. What I want to do is 0.5 times the error plus yes, plus times delta 0.5 let me come up with a training function here. Let's train our model. So to do that, all right. So train if just wanted to return here. Let's do batch is equals to random dot symbol page size, then stats. I want to zip and perfect. I'm going a little bit faster here. Touch. Yeah, well, let's use long tensor, and we have our actions. Set it to 1. All the words. We just use the words here. Yeah. All right, let's set next steps. A float tensor. Next steps. And next. Perfecto. Now I want to go ahead to compute my Q values. So to compute values, I need a variable here. Current will be policy. Stats. Not get yes. Perfect. Next Q values. All right. So it will be contemplating to find the best next action, either to turn go up, right or left. So we're gonna set it up. So we're gonna do next Q values, the one dimension. Next Q is equals to my target net. Then we're gonna do next steps. Let's detach it. All right. Let me set it to 1. Then, all right. Let's go ahead and okay. Expected Q. It's just rewards. What would be let's set up the loss function. All right, let's set up the loss function. Just loss is equals to expected Q. Perfecto. Let's go ahead and do let me do out of this training loop. Now I'm out of this function. Set the training loop. All right, so to set the training loop, I think that's the last thing that I will do. Yes, let's go ahead. All rewards, then we're gonna arrange the range of all our episodes. So my environment, I'm gonna reset it. Then the state. State. So total reward initially to be, remember we want to track this one. So initially I'll set it on 0. So for step in range 500, which is the maximum episode that we have. Yeah, action is equal to select action, then excuse me. All right, next step. Reward and done. This will be action. Let me go do sometimes we need to shape our reward to encourage balance. So I want to do that here by reward plus 1. This will be next. It will be next state. State action reward next state and done. Then state is equals to, this will be just next update, actually next state. Then total reward, total reward, all right, so if we're almost done, I'm almost done here, let's break it. Then what I want to do, just train, let me see. All right, and Yeah. Uh, let's update my epsilon. We want to use the max and times the decay. Node is equals to 0. Then target.net lost it. Dot state date. Yep. Oh, rewards dot append on appends total reward. Let me subtract average reward is equals to with all rewards. All right, this is done here. We want to print our episodes. We want to see how many they are. Then rewards is equals to, we want to just do total rewards in here. Let me just format it. Then let's do average rewards. On last 100 is equals to AVG reward, and also what else should I track here? Let's go ahead and break it if we attain the result that you want. So reward, if the reward is greater than, we said 475, print environment solved. We can also maybe enhance it by printing the number of episodes, but let me go ahead and break it, then run everything. Environment, close, and run it. Oh, all right. So let me just do a quick one to see if there are errors. Of course, there will be, and solve them and run and see what we got. So I'm gonna run first and then okay, and solve these errors. Then run the code one more time and see if we could. Why is it jumping to the end? All right, let me pause the video. All right, so it's running. Episode 47, 80, It's finishing. We're on 205, 219, 300s, 37, 400. Yes, it finished. But you can see from my results, I'm tracking. The agent was doing well. The total reward was 70. We were catching, we want 475. And it was doing well up to episode 9 with 107, with 177 here. And episode 3 went to 227. And now it dropped to 62, 250, 369. Let's see, 463. This is interesting. By episode 31, our results were 463. Our target is 475. Let's see. It's going down 106, 264, 130. Episode 94, 67. 194, 203, 147. So it's still short of the target 475. So we're gonna see 90. We are looking at the total reward here. 50. It's not going down. It's not going down. 55. Ended up on average 55 and total 67. So it failed to reach our target score of 475, average score of 475. So to do this, what I need to do is to refine this code. I've got ideas that I have, and after refining this code, I'll see how best I can change. Maybe I need to change my learning rate, the batch size also. And also I just need to maybe tune my epsilon decay, mean epsilon, to ensure a better balance between exploration and exploitation. And also shape my rewards. Yeah, I'm gonna play with it and see if I can improve my results. So for now, this is how you do it. And basically we are training. I have a video somewhere here. I'll pin it on the as we start this this tutorial. But thank you for watching, and bye for now. Hello everyone, welcome to my third video on reinforcement learning models. Now this is my third video, and I've done Q-learning, DQNs, and now we are doing policy gradient methods. However, I've also done videos on supervised learning models where I provided a code along tutorial on all these models, from linear regression all the way to polynomial regression. I've also done deep learning models, and I've explained and give code along. Did code along projects on these models, from GANs, CNNs, RNNs, and LSTMs, long short-term memory. But in this video, we are going to do reinforcement learning, and we are focusing on policy gradient methods. So let's jump to our Jupyter notebook and let's get started. All right, we have our Jupyter notebook up, and let's get started. So the goal here is to balance a pole on a moving cut. We for those who know the open cut environment, we're going to use cut pole version 1, and we're going to use PyTorch and the OpenAI Gym to do that. So what we are going to do is to rename this to policy gradient methods. And it's reinforcement learning. Perfect. So what we need to do here is to first things first, import necessary libraries. So even before I do that, let me just do The goal is to balance using policy graded methods. What does success look like? Successful when all right. Success when rewards hit 500. Perfect. So this will be marked down and I'm going to run this. All right. So let's get started. I'll be a little bit faster because I intend all these videos to be less than 30 minutes. But however, if you want a detailed explanation, we can then, I'll give you this code file. It will be in my, I'll provide a link on the description so that you can get the access to the code file. All right, so to import necessary libraries, what we need here is to want to import Gym. We want to also import Torch and Torch. I want also to import Torch. And of course, my NumPy. SNP. And lastly, for visualization, I want to import matplotlib. Perfect. All right. So the Gym environment, that's where we get our reinforcement learning environment. That's where we get our catpole. So Torch, NM, neural network, and also Optim. These are just neural networks and optimization tools. Then we want to deal with numerical computation, so we're going to use NumPy and also matplotlib. I am going to use matplotlib for visualization so that we can see what our code is doing. Perfect. All right, so let's go ahead now to set our hyperparameters. Right, for hyperparameters, we want to set our learning rate. I will set it on 0.01, which is basically how fast the policy network learns. Then we want to set gamma. I'll set it on 0.99. So gamma is the discount factor, basically how much future rewards matter. Then let's go ahead and set the episode count. Now, I usually go with 1000, but you can set 300, 500, depending on your need. So the total number of episodes, like when we're trying to balance this the catpole environment, we need to give it the total number it's going to try. Remember, it's a try and error, so we want to set the number of times it's going to try to balance this. So that's why I'm setting it to 1000. So episode count to 1000. Then I'm going to do render is equals to false. I'll set it initially on false. This is basically whether to visually display the environment. All right, let's go ahead and do our policy network. Perfect. So success, then run this one. And all right, let's do our policy network. All right, so what I'm going to do here is I'm going to do a function. Actually, all right, class, let me do it this way. Policy network. We're gonna set our neural network, then dot module, and then I'll close this one. Then on initial, okay, let me go ahead and action. All right, super. Our neural network. Then softmax. Our here will be self.fc2. Then action. Actually, okay, all right. Actually, I don't need to do this at this time. I'll do self fc2, then linear. So what I'm doing here is defining the neural network, and we're inputting 4 features from the cat paw. Then the okay, let me see. Oh yes, perfect. So what I need to do now is set another forward cell x. Then I'll do, so the x here will be touch dirt. One. Then x again is equals to touch softmax x. Then my dimension here, opposite on -1, then I want to return x. Perfect. So we need to establish our reinforcement algorithm here. So to do that, what I need to do is to do class reinforce. Class, okay, reinforce. Then action dimension, and also policy. Network, our state dimension, and also action. Let's go ahead, self optimizer goes to optim, self.policy, is equals to the learning rate that we set on 0.01. Self.episode, we set it initially at 0, empty. I'm gonna set this one also at 0. So I'll go ahead and set another function which will tell how to which action to select. I'll explain in detail when I'm done typing. I'm just going with the flow right now. Touch the tensor. Set it on 0. Probes. Self-taught policy. State. Distributions. Categorical. Simple. Then episode log I want to return action. Also, let's go ahead and create another function. Update policy. Up. Another class rather. All right, to do that, I'm gonna go discounted rewards, set it on empty list. This will set it on 0. Then for loop here for reward in request. Yeah, self episode. Cumulative reward is equals to reward plus our gamma. We're gonna multiply it by cumulative reward. Perfect. And discounted rewards perfecto. Then what I need to do, counted rewards is equals to touch All right, discounted rewards is equals to minus divided by loss, set it on 0. Let me push it right up at the screen here. Then loss now multiplied by reward. Then right here, dot step, and also I will need self.episode as an empty list, and self is another empty list. All right, so the meat and bones we are done. What I need to do is to visualize so that we can see if we're able to balance this. So let's create a visualization function, which I will just do is, oh my goodness. So what we need to do is to diff plot rewards, then rewards, I want to set the figure size. This equals to set it the way you want, but I prefer 10 by 5. Dot plot $1 rewards label. Actually, label. What do you want to label it? P-sort reward. Then our x-axis, we just want to have an episode. The label for the y-axis, total, actually total reward, and this is a string. This is a string. Perfect. For the y label, what will be the title? You title this the way you want, but let's go training progress, actually off brain reinforce on card pro. Title it the way you want. Also, let's see the legend. And let's show it. All right, let's encapsulate everything into one. So let's create the main training loop. And to do that, let's do environment. We say this code cut for version 1. Our agent is equals to reinforce space. Set it on 0. And yeah, and let's do episode. Set it again on 0. And episode and range now reset it. Then we do total reward 0. Now I'll just put a while true, if render yeah. Let me push it up a little bit. Okay, action. Just to agent dot select. Next state, reward info is equals to action. Actually truncated here. Our total reward so if done, I want it to break. Then let's do our agent update and episode. Only to append total reward. And also I want to print out let's do episode so that we can keep the track of the episodes. Then total reward out of this for loop. What I need to do is to plot rewards. So episode rewards. Then I need to close everything here. All right. So of course, I've done some errors, but let's check. Let's check. So what I've done here is to import necessary libraries. What we have is Gym and Torch and NumPy and Matplotlib for visualization. Set up my hyperparameters and also went on to define my policy network. So I defined it as a neural network, and also reinforce my agent class. So I created a policy network and an optimizer, and also I stored the rewards and log probabilities for each step in the episode. Our actions converts the state to a tensor, passes it through the policy to get action, and also samples an action from the resulting distribution, then logs the log probability of the action for later use in learning. And I also set it up to update the policy. I just set up the update policy rule, and also what we need to do is to plot everything out and also initialize the cut point environment and agent. So what I'm going to do is to run this and see the errors and clean up the errors, and we can come up again back and see what we got. Alrighty, so I'm going to run it and double check all the errors. There you go. All right, so I'm going to cleaned all the errors, so I'm gonna run it one more time. So on the first episode, our total was 15. Episode 10, we have still got 15. Let's jump to episode 50. We were down to 9. Remember, our success criteria is to hit 500. So episode 131, we have 123. When we jump to episode 199, we are starting to balance that cut pull, and so we balanced here on episode 199 and episode 200. We went down again one more time. Then at episode 262, we started to balance the pull. Then we dropped it here, but you can see we are starting to balance up the pull. There you go. Then it dropped one more time. Remember, we've got 1,000 episodes, so let me give it time for it to run. So basically what happens is, we're kind of no longer balancing here. But the cut point environment is basically like this, where we have a moving cut here and a pull, and it either moves right or left depending on how this. If it's tilting to the left, this will move to the left. If it's tilting to the right, it will move to the right. The goal is to balance, or the goal is to hit 500, which means balance in our case here. So upwards of 500, we are balancing now. The model, the agent is learned to balance, and we see it drop a little bit here, but this should work. All right, that's basically what we're doing here, and that's the code along. And what I'll do is I'm going to save this code and have you take a look at it and change it the way you want. Most likely, you're going to reduce the number of episodes and also refine it the way you want. But thank you for watching. See you and bye-bye.